Mm. Hi. So I thought I would do this video since I'm not here today, and I always feel like it's better if you hear me talking at least. So, what does it mean to be a successful collision? What is a successful collision? And how is it different from one that's unsuccessful? And what factors make a collision more likely? So we talked about the fact today that collisions are really effective collisions. Successful collisions are really not all that common. No, that it's really hard. The only thing that saves the whole operation is that there's millions, billions, and trillions of particles that are colliding. All right, that the time scale at the atomic level is so much faster than with tiny, tiny particles than it is up here at the macro level. So the model of collisions between particles explains the speed at which reactions transform reactants into products. And this is called the reaction rate, as we discussed yesterday. So the key idea is that for reactions to occur, the reactant particles have to collide to break the bonds. So we looked at this with water, and we found out that, well, we said it takes 1,370 kilojoules to break all the bonds in the two H2 molecules and the one O2 molecule, but that's what we thought. We just had to supply the energy, but no, they have to collide, and the orientation in which they collide that this successfully works in this reaction is one in which you can see they collide in a way that we can actually see the potential water molecule right there. All right, so how many times do you think these collide before they reach anything that successfully gets 6 atoms in just their correct orientation so that they can form 2 water molecules? So you can see that the problem here is that colliding is one thing, adding energy is another thing, but being able to move rapidly and collide in just the right orientation is difficult. I was indicating in the previous lesson that it was as though we were karate chopping the bonds. But in fact, as you can see, it's much more complex. So the reaction rate's higher if there's more successful collisions. All right, so the important factors are as many collisions as possible and as many highly energetic collisions as possible to increase the chances of reactants colliding in the best place on each molecule. So we're going to look at these factors at the level of particles and the ways in which these can occur. So the first is having more collisions. So the higher the number of particles, the higher the probability of having a successful collision. So it doesn't necessarily mean super advantageous. It's as if you bought 1,000. Well, let's say first you bought 100 lottery tickets, and that gives you a much greater probability of winning than 1 ticket. But since the odds of winning are 1 out of 6.5 million, 100 tickets gives you a higher probability, but you don't know if it's going to be enough to be successful. All right? So that's the idea that we're going with more collisions. So how do you get more collisions then? How can you create a reaction that has more collisions? Well, we look at these 3 example containers, A, B, and C, and what you guys intuitively noticed was that, well, the one that has the most particles is most likely be the one where there would be the most collisions. So if we were a crowd and there was a crowd of the density of C, we realized it would be possible to bump into people more often. So most particles would lead to the most collisions. All right, so see how this pretty much relates to our common sense into understanding of really bumping into people. All right. So let's see. So which of these I want to introduce you to this concept. Which of these shows the concentration, the highest concentration? So, a higher concentration of each kind colliding at one time increases a chance. So the word here that's different, that is a very chemical word, is concentration. So, when particles are closer together like this, more particles in a space, that means a higher concentration. That equals a higher concentration. That's how we use that word in chemistry. A higher concentration of whatever the particles are. So it increases the chances of having a successful collisions. All right, so which of these containers, A, B, or C, has the highest concentration? Which has the lowest? So fill that out. And then write what the rule is then. So we just went through, I want you to paraphrase the rule we determined. The rule to getting more collisions, which is our theme here, is, and you finished this based on what we just talked about. All right, go. So all you have to do is go back up here and look and paraphrase what you saw. Then we move on to another way to get more collisions. All right, another way to get more collisions. Well, the state of matter depends. So the freedom to collide is based on how well particles can move. So the issue is freedom to collide. So we're going to look at the motion in solids, liquids, and gases, which you already know from this diagram. All right, you know that in a solid state of matter, what these do, these particles jiggle up and down. All right, but they aren't really free to move. They're attracted to each other, highly attracted to each other. That's the reason that they can't separate. And that's somewhat true in the liquid state. They're still highly attracted, but there's more, there's more motion. What's happening in the picture? All right. So I'm very puzzled because we've lost our picture. There it is. Okay. So as much they're highly attracted to each other, and they still are in liquid state. You can see there's more freedom of motion. But when we get to this gas state of matter, we can see much more freedom to move. All right, the key factor, freedom to move, because it's hard to collide if you don't have freedom to move. Little attraction, if any. And high-speed motion from here to there. High-speed motion from here to there. That's called translational motion. From one place to another. All right, they're moving randomly, of course. much more freedom to move, little attraction, high speed motion from one place to another. All right, so solids have these particles close together but not free to move. All right, and that's what this paragraph is saying up here. Only the surface particles are really able to collide. That limits the collisions of a solid reactant. So, dissolving the solids, however, increases their movement and distribution. Secondly, particles in the liquid state have more freedom to move. Particles in the gas phase, as we've seen, move more than liquids and at higher speeds. Now, collisions are more fruitful if they are closer together. So let's look at these pictures below. You know, we can press particles closer together like we do in a cylinder. So in the engine, when it expands and then it pushes down on the particles like this to make them into a smaller volume, and then there's an explosion in the gas tank, a controlled explosion. All right, that is what keeps the engine going. But in a reaction, we can do the same thing. So we can add more particles, increase the concentration like we did, or we can press the ones we have, the same number of particles, closer together. So pressure affects the rate of reaction too. So when you increase the pressure, as shown, the molecules have less space, so that greater density of molecules increases the number of collisions, all right? Which thoroughly makes sense. So it's another crowd phenomenon, but instead of it just being more particles, we close the amount of space that the same particles are in. By decreasing the volume available, there are more collisions. So what is the rule? The rule is, all right, the rule is to get more collisions, we must, all right, so tell us, what did you learn in this lesson? Go. All right, another way to get more collisions. So we're still on the theme of increasing the number of successful collisions by having more collisions. Well, what about the greater surface area of the reactant increases the frequency of collisions? This especially affects solid reactants. So how rapidly particles are released to collide depends on whether they're in lumps, granules, solutions. The greater number of particles able to collide at any time increases successful collisions. That's why dissolving a solid makes the collisions more frequent. We said that it was clear to us that it was the precipitation reactions that were so fast that we put in solution. All right, so let's put that. We poured 2 solutions together. Of ions together. They were both ionic compounds and had a super fast response. Super fast rate of precipitation. All right. It was immediate, it seemed to us. All right. So, So we are responding to this idea that, yes, we could agree that dissolving a solid makes the collisions more fruitful because this is what we saw in our experiments. All right, another way of doing it is see how the particles able to react are these red particles. All right, so we see them throughout, but only the ones on the surface are able to collide with another reactant, right? But what if we arranged it this way so there are many more particles, red particles, 4, 8, 12, 16, 20, all right, 24, 28, 32. This time there's 32 particles that are on the outside, and we did that just by breaking apart the chunk. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There were 19 particles able to react and 32 exterior particles here. So simply by crunching it up a little, we were able to get a greater surface area. So this sort of thing, 32 would have more collisions because there's more particles available. Because more particles on the surface. The inner particles can't react. All right. So reading this caption, it says, in these figures, only the particles on the outside of the solid blue have a chance to collide with the red reactant. In figure B, the same amount of solid reactant is used as A, but crushed into smaller particles. That means that more particles on the outside have an opportunity to collide with the reactant and speeds up the reaction. All right. So, 19, there are 19 particles that can seem to, the reactant that can seem to react with this, whereas there are 32 over here that could react with the blue reactant. I may have misspoken before. All right, so what's the rule here that we found? The rule is more collisions happen because, all right, you write the answer. So when I make these videos, the idea is that by me talking you through these things, it becomes less difficult for you than reading through it yourself, because I'm putting the emphasis by my voice and my writing to make it more understandable. So why don't you take a minute to finish that, and then we'll move to the next section, which isn't about more collisions, it's about energetic collisions. All right? So we have a different theme. Go ahead and finish the rule. Be sure your cell phones are in your backpack. Because remember that the key to getting a higher grade is understanding what's going on. All right, and really being with it as we work through things together. All right, the second part, the first part was more collisions. The second part is energetic collisions. So in the successful reaction, one factor in energetic collisions is they have to overcome the activation energy. All right? Yeah. All right, so here we have an exothermic, and here's the energy of activation. All right, and here we have all right, so both kinds of reactions, whether the reactant is high and the product is low, or the reactant is low and the product is high, in both kinds of endo or exo reactions, we know perfectly well we need an activation energy to break those bonds. So in the successful reaction, one factor to overcome activation energy is energetic collisions. So how does this happen? How do you get more energetic? So all of these things are going to be about getting more energetic collisions. High speed, head on, and that by head on I mean at the right place, are more fruitful than glancing blows because collisions occur with greater energy. So a head-on collision with another person in the hallway is a much deeper kind of collision than just having a glancing blow when your elbow hits somebody else's side. All right, so we're talking about fruitful collisions that are energetic in actually, colliding, genuinely colliding. So, more energetic collisions, particles in the gaseous phase move faster. When these particles do collide, it's likely to be energetic. So, gas phase, remember, they are farther apart, but they are also able to move 1,000 to 2,000 miles per hour. Hydrogen moves very fast. Oxygen, not as fast, but pretty fast. So, what is the rule to get a more energetic collision? Energetic collision. Collision is, and finish that out. What's the first rule we're discussing about how to get an energetic collision? And now, oops, I spoke too soon. Take another 30 or 45 seconds. All right, more energetic collisions. Well, a higher temperature at which reactions occur increases the energy of the collision. Oh, well, that's pretty significant, isn't it? Higher temperature. Higher temperature. I think I'll underline higher temperature. So that's in fact a great factor because people are, that do reactions for a living to create a product, the temperature is a critical factor. So if you have a higher temperature, it increases the energy of the collision. When higher temperature, then the particles are moving faster. You know that. All right? Meaning the particles hit each other harder. It's like a collision, two cars colliding head on at 30 miles per hour compared to 70 miles per hour. You know it's a much harder hitting collision when the particles are moving faster. So that increases the energy of the collision. So at a high temperature, the particles are moving faster, and that's what these vectors are showing. All right? The length of the arrow shows the speed. And you can see at low temperature, the particles have much smaller vectors, and they're clearly not moving as fast. All right. So that increases the energy of the collision when you have fast-moving particles. So the rule is to get more energetic collisions is all right. So let's paraphrase what we just talked about. The more I get you involved in writing and thinking, the more you're likely to remember this, and the more likely you're to understand as we go along with it. Okay, the third emphasis, all right, we've had increase the number of collisions, increase the number of energetic collisions. Now, it's to increase the collisions that are at the right orientation. They hit at the right spot. The reacting particles must have the correct spatial orientation. Of course, we're talking about a three-dimensional collision to break the old bonds and form the new ones. So, better oriented collisions. To orient means to position somebody or something facing in a particular direction. So when I talk about the orientation of the hit, a car can hit head on, a car can hit from the side or the back or at an angle. All right, so there's many ways a collision can occur, but the orientations when the particles occur either work or don't work. And of course, we know most of the time they don't work. So to orient means to position somebody or something facing a particular direction so that the collision works better at the particle level. So what factors actually do that? Well, the presence of a catalyst. Enzymes are catalysts in the body. The presence of a catalyst increases the likelihood of the correct orientation for collisions. A catalyst provides a surface that interacts with individual particles. So they hold the particles in the best position or orientation to have a good collision. That's how a catalyst is able to increase it. So the reactant binds to the catalyst, and by the way it's bound at one end, the other end is sticking up. All right, so here's an example catalyst. And so, see how the reactants are bonding to that funny shaped catalyst. And then, because they're there, they're able to unite. They're close enough together to be able to be attracted to one another in a chemical bond. All right? And then they're released from that enzyme. So, enzymes in the body are the catalysts that make reactions occur at a physiological temperature, at our regular temperature of 98.6. So catalysts and enzymes are very important in the human body. But in reactions in general, reactions that are difficult to happen, if you can find a catalyst that will perform this kind of homing pigeon kind of thing where they go to the right spot and then the reactants happen to land correctly, that is amazing. All right, so enzymes are the catalysts in biological system to hold reactants in place. And they're large covalent molecules, all right, huge. And because of their huge size, that's why they're able to have these little pockets on them with places, all right? and they help in the orientation. So what is the rule about a catalyst? But why does it help orient? The rule is for correct orientation is, and explain why that would function. All right, take a minute to do that. Okay. Now, I want you to summarize all these rules. All right, so we have 1, 2, 3. All right, so I want you to say, for example, the first one is more collisions. All right, what's the second one? What's the third one? And then write a summary of what the ways are to get more collisions, what the ways are to get more energetic collisions, and what the ways are to get better oriented collisions. And when you're done with this, would you come on down and look at these pictures? So the question really is then, look at these pictures and then think about answers to questions 1 and 2. Remember, I have a higher opinion of your thinking and figuring out than you do. All right, just look at the pictures, read through the diagrams, think through what we did, go back and read, but just answer these questions. That's what it takes. There's no point in being intellectually lazy. I mean, we're here for some time together today, so just use it. For those of you worried about your grade, you just have to think through things. All right? There's no point in thinking that you can push it off to later because we've kind of reached the end here. All right, I'd like you to finish these. Thank you for listening, and I hope you're having a very good day. All right, talk to you later. Bye.